Hey guys, and welcome to our video for practicing to graph a polynomial equation. Now I'm not going to ask you to graph a polynomial equation in standard form unless it is, as in the last video, something that is easily factorable to get into a factored form such as this. Okay, so to do this, remember we need four things to graph a polynomial. We need its degree, leading coefficient, the roots, and their multiplicity. So we look at this, what is its degree? Now, we need to identify whether it's in standard form or factored form. If it's in standard form, degree is easy, it's just the highest power. But this is in factored form. So for factored form, we want to add up the multiplicity, we're going to add up the powers, the exponents on each factor of x. So since there's an x here, we can say there's a 1, this has a 2, and this is a 3, so we get 1 plus 2 plus 3. That gives us a degree of 6. Now our leading coefficient is 5. It's simply the number in front, right? The leading coefficient is 5. Now what does that tell me so far? Pause the video, think about it. What does that tell me? That's right. That tells me my end behavior. Now because my degree is 6, which is an even number, my leading coefficient is 5, which is a positive number, I know my end behavior is that both ends are going up. And that's how easy it is. Now we want to identify our roots and our multiplicities because that will tell me what's happening inside of those end behaviors, right? In that dotted area. So we can just go left to right. We can go kind of figure them out and then write them down in order. It doesn't matter. I like to just go left to right because it's easy. So our first term we have 5x. Is there any value of x that will make that 0? Well, yeah. Because there is an x here, 5 times 0 is 0, so x equals 0 is a root. Now, we could list all of our roots, then go find our multiplicities, but it's just as easy to do it simultaneously. So this factor here, which gave us our root at 0, has an exponent of 1, so it has a multiplicity of 1. Our next factor, x plus 3. What value of x will make x plus 3 equal 0? That's right, negative 3. And that factor is squared. So that means our root at negative 3 has a multiplicity of 2. And lastly, we look at this last factor here, which is x minus 2 cubed. What value of x makes x minus 2 equal 0? Sorry, just a nice easy 2. And that factor is cubed, which means that occurs 3 times. So our root at 2 has a multiplicity of 3. We have everything we need to be able to sketch a graph. Now notice on my graph here, I don't have any labels on my y-axis. When we're sketching graphs of polynomials, we're not concerned with how high these are going. We're only concerned with kind of where they're going up, where they're going down, and where the relationship is with the x-axis. If we need to find out how high something's going, we can do that in other ways, okay? By just testing things, using our graphing calculator is really the most common way to do that. So now we have all this. Now we can graph this. What's really nice is this is really easy to do. I always like to start out by kind of hard dotting my roots. Just something so that when I'm graphing, I have a visualization of where I'm going. So we have a root at negative 3, 0, and 2. Okay? Now, as we talked about our end behavior, we have a even degree, positive leading coefficient. So our end behavior is both going up. So to start this, we simply start out here. We want to go beyond our last root, okay? We want to start wherever our end behavior is. If this was, say, a negative leading coefficient or an odd degree, right? So something where this end was down here, then I would have just started by drawing an arrow down here like this. Now, as we're coming in, we want to look at each of our roots and look at what their multiplicity tells me to do before I get to them. I don't want to get to it and then go, okay, what does my multiplicity say? Because if I get to it like that and my multiplicity says, oh, you need to bounce off, I don't V off. I need to slowly curve in. If it says you need to flatten out and go through, well, I can't hit there and then flatten out and go through. That would be right, because the 0 should be in the middle of that flat spot. So if we look at negative 3, the root at negative 3 has a multiplicity of 2. So that tells me my graph is going to bounce off. So I just simply need to take my graph, bring it down, and bounce it off. Now, I didn't carry on beyond that much further. And the reason I did that is because I want to stop. This root is done and dealt with. I want to look to my next root. I want to see, because if my next root is at negative 2, I need to very quickly turn around and do it. I don't want to have to I don't want to be like, well, it bounces off, and then I don't want to have to erase a bunch of stuff to do my next piece. So our next root is at 0, and it has a multiplicity of 1, which is really nice. So that means that all I'm going to do is I'm just going to go through my root at 0 in a linear fashion. In other words, I'm not flattening, I'm not bouncing, I'm just kind of going through it. Okay? So what we want to do, again, this is just a sketch, so I don't know how high this goes. I don't know if this thing shoots off way up there or if it barely clears the x-axis. But we can just draw it like this so we get a good visual of what's happening. And so I just kind of came up and I come down to my x-intercept at 0, and I go through in just kind of a straight linear fashion. Okay? Now my last root is at 2, and that has a multiplicity of 3. Multiplicity of 3, that's odd and bigger than 1. So what that means is I'm going to flatten out and go through my axis. Okay? And so all I'm going to do here to graph this, I'm going to go down, back up, kind of flatten out there, and move on. Okay? Now you can exaggerate that, flatten out a little bit more, but we don't get too crazy, right? We don't want to come up here, flatten out, and go like that, right? It's just kind of a little bit at that spot. Now, there's no more roots. I'm done. There's no more roots left to do. Since I have no more roots left to do, I go to my end behavior. Okay? Remember, the end behavior only tells us what happens on the very ends of our graph. Inside there, everything else takes over. So since I've gotten everything inside, now I want to look to my end behavior, which degree 6, leading coefficient 5. So even and positive, both ends are going up. So that end goes up. Now, in the past, I've had some students that when they identified the end behavior, they put both tick marks in. And that's fine. That's actually kind of a great way to do it if you're not sure if you're going to mess up something in there. Because if you have this end behavior going up here, but this last piece ended down here, it can't get back up. Now, let's talk about why it can't get back up. Why can this graph not cross right here? I'm doing it lightly because I don't want to. Why can I not cross right here? I can't cross right here because to cross right here means I cross the x-axis, which means I have a root or a 0 or an x-intercept, but I don't have one there. So if you don't have a root, x-intercept, or 0, as defined by the function, you cannot touch or cross that x-axis. So that means we can't do that. So that's why if we ended up somehow messing something up and being down here, when we know our end behavior is supposed to be up, we can't just go like, oh, well, I just turn around and go back. Okay? So that's what we get. That's it. That's how easy it is. That's how simple this is. Now let me ask you something. Can you solve that inequality? Based on this function f of x, I want to know the answer. When is f of x less than 0? Well, what does that mean graphically speaking? Because if I think symbolically, that's a lot. I'm going to have to, okay, I found my roots. All right, now let me create my table, find the intervals, pick a test point, test that value into this crazy thing, get that value, check it. Seems like a lot of work. But if we can use a graph, I mean, you saw how much work I went into creating a graph. As you get more comfortable with these things, it's going to be even easier and easier and easier every time. So if I can think about how to solve this based on a graph, it makes it easy. Now if we remember what f of x is, back to function notation, right? F of x equals y, which means the y values, or our output values, are the f of x values. So this is just simply asking, when is our graph on the y-axis, right? When is it less than 0? What that means is simply, when is our graph below the x-axis? That's easy, right? There's the x-axis. I look, I'm below the x-axis right there, and that's it. Which means I'm below the x-axis. Now right here we touch, but we never go below. If this was less than or equal to, I would have to include this single point. But because it's less than, we don't have to. So for this to be, for our solution here, we just simply need to cover this interval. And whenever we're talking about this, we're always talking about the x values that make this work, right? So what x values work here? Interval notation goes from smallest to largest. So we'd start at 0, and it goes to 2. And then I just have to ask, do I want to include those points or not? Since this is just less than, we don't. Boom. That's it. We just solved when this polynomial function is less than 0. Only on the interval from 0 to 2. That's all it is, guys. That's how easy graphing polynomials can be. That's it. And I'm not oversimplifying it with a simple problem. That is really how easy it can be. So let's do one more. So I'll just recreate this. Alright, so I have negative 3 times x minus 4 squared times x minus 1 times x plus 2 squared. So we need to go through and identify our degree, our leading coefficient, our roots, and their multiplicity. Okay, so the degree, since this is in factored form, we just need to add up the exponents. 2, 1, 2. So 2 plus 1 is 3, plus 2 is 5. And our leading coefficient is the number out front, negative 3. So we have an odd degree, negative leading coefficient. So that means that our function is going to have this end behavior. Next thing is the roots. Okay? We go left to right. So I have negative 3. Do I have a root at 0? No. Because there's no x here, I don't have a root at 0. We don't always have roots at 0. Only if there's an x by itself out here. So our first one comes from this. So when is x minus 4 squared? When does that equal 0? When x is 4. 4 minus 4 is 0. Now, since that came from this factor, and this factor is squared, that means it has a multiplicity of 2. Our next one, x minus 1, what value of x makes that equal 0? 1. Since that only occurs once, it has a multiplicity of 1. And lastly, when does x plus 2 squared equal 0? And that's when x is negative 2. And that factor has an exponent of 2, so we have a multiplicity 2. All right, now I'm going to draw out my axes, and I want you guys to try and graph this by yourself. Pause the video, try and graph this. You guys finished graphing yet? I mean, you paused it, so you should be, right? All right, so cool. We're done graphing. Now, using this end behavior idea, degree and leading coefficient, we know that it is an odd degree. So we know that the two tails go in opposite directions. That was something I didn't mention before. Mention it now, so pay attention. Odd degree, our tails are going opposite. Even degree, they go together. So x cubed would look like this. But since this is negative leading coefficient, I'm going to start out up here. Okay, perfect. Now, I want to go through and hard mark these. So negative 2, 1, and 4. And I also marked a tail out beyond that 4 because that is my last root, and so I just put that tail for the other end of the end behavior. So I know if I end coming up here somehow, I know I did something wrong. So let's graph this. You simply come in, our first root is at negative 2. Negative 2 has a multiplicity of 2. That is a bounce. So come down and bounce off. Easy. Our next root is at 1, which has a multiplicity of 1. Multiplicity of 1 means we go through in a kind of linear form. So that. And lastly, we have 4 with a multiplicity of 2. Multiplicity of 2 is even. Evens bounce off. Bounced off. That's my last one. I'm below. We're happy. Connect that to our end behavior. We're done. That's it. It's that easy. It's so nice. It's so smooth. Yes. All right. Now, this problem here that we're about to do is one of those ones that I'm doing because I want to show you both things, but also because this has a very weird thing that happens, and I want to mention how to do it. So, I want to solve when f of x is greater than or equal to 0. So all I'm looking for is when my graph, since I'm looking for it to be greater than 0, when my graph is above the x-axis. And I see how that works here, and that's here, okay? But because it can also equal 0, I want to include anywhere that it touches, which is here, which that's just a part of this interval, that's good. Here, which is just the end of that, so that's easy. But then we have this one point over here, so that's weird. That's going to be the weird thing. But let's start with this other part. That's the easy part. So what's the smallest x value that this is above 0 for? Well, everything negative, right? So our solution starts out at negative infinity. So moving along, we're greater than or equal to 0, we're good, we're good. Ooh, we touch, but touching's okay because we can equal 0. So that's okay, we're still good. We touched, oh, but we dropped down. So we need to stop here at 1. So it goes to 1. Now since I can include 0, I simply bracket. Okay? Now if this point wasn't here, if this stage went off and we're done, this would be our answer, we'd be done. But there's more, so we need to have a union. And now this next piece is the weird thing. And this is something that doesn't happen very often. It's pretty rare. It's usually only when a teacher does it, and sometimes it's just by mistake, sometimes whatever, but you need to know how to deal with it. How do I include a single point in an interval? Because I can't write it as like the point 4 comma 0, because this is interval notation, and that would mean like I would be doing the interval from 4 to 0, but backwards, which is supposed to be 0 to 4. It doesn't work. The way we do it is we use brackets. Okay? So we're going to have a bracket, we're going to start at 4, which means I go all the way down to 4, and I include 4. But this interval just goes from 4 up to 4. Because this means that I go all the way up to 4 and I include 4. So this interval, the only thing that's included here is the number 4. So if you ever have to include a single point in an interval answer, this is how you do it. Okay? If I said when does f of x equal 0, do not write bracket -2, close bracket, union, bracket 1. No. Right? Only if you include a single point in an interval answer like this. Alright, you guys. That's it. Short video for you. Next video is going to be how to go from a graph to a function. We'll do that in just a minute.